Thank you very much. Thank you very much for this kind introduction. I think you see my screen. I just wanted to open Teams because we already have the first question by Eddie Cruz. Will the PowerPoint be available after the presentation? It is actually available now. You have to already in the chat 2 links that should work, both of them, to my OneDrive. So you should be able already to download both slides in PDF and the code I will be showing. So now it's time to start with my presentation, Predictive Analytics with Transact SQL. I am Dan Sarka. I am really glad and honored that so many people registered, and honored that I'm speaking in this for this great community. I'm pretty long working in this area, more than 36 years, already 30 years or so with SQL Server. I'm Microsoft certified trainer for 25 years, most valuable professional also for more than 20 years. And I authored and co-authored 19 books so far. I focus in this area, SQL Server, data science, data quality, data modeling. So what I will talk about is I will do a short introduction. Why would you use Transact SQL for things that usually are solved with Azure machine learning, Python, R, and what can you do in Transact SQL? And then I will talk about 3 algorithms: k-nearest neighbors, lookalike model, and Bayesian inference. These things are more in detail explained in my last book, Advanced Analytics with Transact SQL. So there is also there are also many other things explained about statistics, machine learning, and so on. So first of all, why Transact SQL? Of course, we know that Transact SQL is not focused on machine learning, on data science. So it looks like a little bit far-fetched to use it for these tasks. However, many times you need to do a little bit more digging for, let's say, 1 or 2 reports, and you don't need or don't want to become a full data scientist. You know, like learning a new programming language like R or Python, or new services, Azure machine learning, that of course can also run either or both Python and R. Of course, these take time. These take time and resources. So you might spend a couple of years before you are really good at it. And maybe you already use a lot of Transact SQL. In addition, what if you have to deal with huge amounts of data? This is nowadays many times a fact. Of course, you cannot do really in-depth analysis and very complex algorithms with billions of rows. Typically, you still work on samples, but some things can already be done on huge amounts of data. Of course, in Azure, you can simply add resources, but at some point, the price becomes unbearable. The good thing is that you can use some fast engines. Now, what do I mean by fast engines? Are R or Python slow? Actually, they are not slow unless you work there with row operations, with loops. Then they are just as slow as Transact SQL. In R or Python, you work with an object that is called data frame, which is something in between a matrix and a table. So matrix 2 by 2 matrix is limited to a single to values of a single data type. Data frame can have columns with different names and different data types, similar to a relational table or relation in SQL Server. However, you still have positional access and order is preserved. So it's kind of advanced matrix or something in between matrix and a table. And R and Python have very fast matrix operations. R is built in the core engine. These are built in the core engine, these matrix operations. In Python, you get them with the NumPy library, and then on the top of it with Pandas library, you get the data frame. So working with data frame instead of working with loops in R or Python means like 50 to 100 times faster work. Still, working with tables in SQL Server could add additional boost of at least 10 times. So you must realize that SQL Server, also other relational database management systems like Oracle and DB2 are optimized to work with huge amounts of data for decades. And this is practically the only thing these engines do. R and Python have, of course, hundreds of different libraries and functions, thousands of functions to do some statistical analysis, data mining, machine learning analysis. Transact SQL has, on the other side, very few statistical functions, aggregate functions. But as I said, it can be magnitudes faster than R or Python engine. But of course, we have these limitations. So I will show you what you can do, some things, some basic algorithms using window function and some advanced Transact SQL features. Main issue here is that typically we have complex calculations that need some pre-calculations and then they work in loops. So what we want to achieve is minimal number of passes through data or scans through data, maybe a single pass, single scan, and do whatever we need. However, we know that we should avoid cross joins. This will also give us unacceptable performance. I will go through algorithms and show examples. Of course, you can then try to improve performance additionally with column store indexes, but don't forget, many times these algorithms work even better with samples than with really huge amounts of data. So sampling is the core thing in statistics. Now, after this introduction, let me start with the algorithms. And I will use k-nearest neighbors algorithm only for an introduction. Actually, we will get at the end two useful algorithms, lookalike model and Bayesian inference. But KNN is a core idea behind a lookalike model. Lookalike is kind of KNN plus decision trees. So I will start with KNN. Initially, it looks great. This algorithm is called lazy learning. It simply means there is, even lazy learning is too much. There is no learning at all, training the model. So what does it mean, training a model? You have a data set, and then you implement algorithm on this data set, and the result is then stored in some kind of a table result where you see some things like maybe people that are older, live in suburbs, have higher education, typically buy more cars. This is kind of a result of implementing an algorithm on data, and this is called a model, data mining or machine learning model. So training or learning is the process of creating this model, and KNN is lazy learning, or even better said, no learning at all. We just have the data set, and then we have a new case, and then we use input variables to find k cases, like 10 cases that are the closest to this new case. And then we have target variable. We use average or median or whatever statistical value of this target variable. It can be even a discrete, so we can even use for discrete variable the distribution of this discrete variable in this set of k cases. And then we use this value average or median as a prediction for this new case. Small k means you can have very high variance, a large k decreases variance but kind of raises bias. This algorithm is prone to give you what is called local maximums, values that are more or less randomly very clear, but due to the random position of cases that are kind of accidentally close together. Now, typically with KNN, we work with continuous variables, which can have very different scales. So the first thing that you do, you scale the variables with z-score normalization. Scale, I will show you this in example, and you will understand immediately why normalization is needed. Z-score normalization is from every single value, you subtract mean of the variable and divide this by the standard deviation of the same variable. And with z-score normalization, the new variable has mean at 0 and standard deviation at 1. So all variables that are normalized have the same mean, the same standard deviation, so they are on the same scale. And then we have a new case, and then we search for k closest cases. So let's start, let's say in this example, we can search for K3 or for K8. And then for these cases, we calculate, let's say, the average of target variable. And we say that this is our prediction. Now, you can use different measures of distance. So typically we use Euclidean distance, very well-known measures of distance are also Chebyshev distance and Manhattan distance. I will use Euclidean distance in my case. Now, the problem here is that I said we need to find distances of new case to this k case is selected. But I need to check which cases are the closest. So basically, I have to check the distance of this green case to every other case in the data. And let's say that this is one case, but let's say that I have in the training data, let's say 100,000 cases, and I have 10,000 new cases. Basically, to find the distances, I am actually doing a cross join between these two tables because I have to scan for every case in that search set. I have to scan the full training set. And let's maybe see if we can help ourselves with geometry data type and with spatial index and see if we can somehow make this better performing. So I will start first with data preparation, and you will see later this idea of KNN will be very useful for look-alike model. So I will use retarget mail view. My target variable is a flag bike buyer, whether a person in the past has purchased a bike or not. And I have a couple of discrete variables like region, commute distance, and two continuous variables. Here, last but one, this is age. And also somewhere earlier, I have yearly income. And of course, you can see that these two variables have completely different scale. Yearly income is measured in $10,000s, age in years. So if I don't scale them, yearly income will completely overwhelm age, will be practically the only variable used. And my initial used for prediction. And my initial state is I have like 51% non-buyers, 49% buyers, approximately 50-50. We will also measure the lift or accuracy of our predictions. So with randomly taking cases, out of with random guesses, we would get approximately 50-50 distribution. Now, how do I create scaled versions of input variables? So I need to subtract average and divide by standard deviation. And I'm multiplying everything by 1.0 to get decimals from integers. You will say here I have a cross join. Yes, that's true, but this is not actually a cross join. I could use also a common table expression here. This is cross join with a single row. So I'm basically adding these values to every row in the select statement. So I can use them for calculations. I could also use window functions, but then this would be more code. So I prefer this version. So here cross join is quite useful. So I have age, income, and I have age scaled and income scaled. Now let's check the distribution of scaled variables. So now I'm calculating these scaled variables in a common table expression, just then to calculate the aggregated values. So minimum, maximum of age. Average, you see, is something small multiplied by 10 on minus 8. So it's practically 0. Standard deviation is practically 1. Min max of yearly income, it goes from minus 1.5 and up to plus 3.5. And also standard deviation is 1 for income, and mean is again very, very close to 0, even closer. So I can fix minimal and maximal values for both variables at -2 and +5. This is important for spatial index. I need this bounding box. Now I will create a geometry version of instance of these two input variables. So I will use values of input variables as coordinates in this two-dimensional space. I'm using only two input variables. So here are my points. So every single case is now converted to a point. Now I will prepare training. First, I will prepare the data, full data, not split it in training and test set. I will just, I will simply select everything into a new table. So besides original data from the target mail view, I have now also my geometry data instance and scale to variables. You see, I'm working on 18,484 cases. So here is my complete data, original data, scaled variables plus geometry data type instances. Now, before I do any predictions, I want to continue with a lookalike model. As I said, lookalike model is based on KNN practically, but it uses also one small idea of decision trees. I will now use not continuous variables anymore, but discrete, and I will also discretize age and income. Now, the most popular data mining algorithm for classification is decision trees. I will just briefly describe this algorithm, and then from KNN and decision trees, we will create lookalike model. So decision trees classify each case of a new case to one of a few discrete categories of target attribute. So we explain then this classification with input variables or input attributes. Decision trees are very popular in data mining because they are easy to understand. And of course, they are pretty good also doing predictions. The algorithm used is called recursive partitioning. And yes, we already see another big stop sign recursion not something you would like to implement in Transact SQL, right? So this simply means you split the data into partitions and then you split up more. So you start with all cases in one big box, and then we use every single input variable and split these cases in classes of input attributes, and then we decide which split is the best based on purity of distribution of target variable. So to go back to our simple example, we have bike buyer, two states, initial distribution is approximately 50-50, and then let's say that we have two different commute distances, close and far away, let's say, and we see that after splitting in these two classes, the distribution of bike buyer in one is 30-70, in another 65-35. And if we take another distribution, maybe house owner flag, another input variable, house owner flag, the distribution of the target variable might be 60-40, 55-45. So apparently the first split was better because target variable was purer in the classes of input variables. This probability or frequency distribution works well if target variable has two states. If it has more states, then we can use entropy, Bayesian scoring. So this could become a little bit more complex. And then we repeat the splitting, again, testing all possible breaks. So where do we stop? We have problem that we get results that are too good to be true. Just imagine that we come to the classes with a single case. Target variable can have only one state there with 100% probability. So we would get really, let's say, good predictions, but with a lot of bias, of course. Now, this is an example. So I have asked people how did they like some of our products, and we see that initially 55% of people liked it, and 45% of people didn't like. So here we have, and then we made first split at age of 35, and after the split, older people 73%, older than 35, 73% of them liked, while younger people 67% didn't like. And then I continue the split over education, and I get more and more groups. And of course, maybe at some point we decide that some of these groups are not really useful. If you look at this top left group and bottom right group, these two groups have very few cases, so probably these two groups are not so useful, so we don't use them for prediction. If people are from this group, we use for prediction one branch above. Now, of course, this recursion is impossible in Transact SQL. I mean, this would take ages. So what do? We simply do the split to the end, and then we just, with the new case, find appropriate group. And we can do this very efficiently. So there is no recursion at all. We just need to find groups, to define groups based on values of input variables. Let's call this new variable grouping factor, something that is combination of input variables. What we are doing, we are calculating target variable distribution in classes of input variables. So we have, for example, here region, North America, Europe, Pacific, and we see that we have this gray blue is buyers. We have more buyers in Pacific region. Yellow is non-buyers. And for example, number of cars owned, we see that with 0 and 1 car, we have more buyers than non-buyers. With 2 and more cars, we have more non-buyers than buyers. And so on. So this is what we are doing. And one more thing from theory. So I need to somehow measure how good my model is. Actually, there are many, many measures, but I will use something very simple, what is called confusion or classification matrix. So I have two states of target variable, and I have two possible predicted states. And if I predicted negative value and the value is actually negative, then I am in this true negative class. And then I can have false positives, which means I predicted positive and actual value is negative. And I have false negatives, predicted negative, actual value is positive. And I have true positives, predicted positive, actual positive. And out of this, I will calculate accuracy by adding true positives and true negatives and dividing by all four together, or also by the total of number of cases I used for prediction test cases. So this will be calculation of accuracy. Now, grouping factor, I can simply concatenate values for a couple of input variables, and I can even do some binning. I have to take care that I don't get too many groups with very few cases. I would prefer to have all groups with more than 10 cases if possible. And what I will do, I will, for example, commute distance group from five initial classes into three new. I will just keep the original three classes of region, and I will also use the entire function to bin income into three classes, and also number of cars owned will be then binned into three classes. And this will be, so I will use in this case 4 input variables, and what I'm doing here, I'm grouping by group factor and ordering by count of cases. And I see that I get altogether 76 groups, and most of them I ordered by count of cases in groups. Most of them are useful. First 10 probably are less useful, or first 9 are too small, and predictions that I get from these groups, I would probably disregard them. Now I will split the data into training and test set. So I will teach or train the models on training set, and then I will check how good they are on using the test set. I will create 30% of data for test set. I will use crypt-gen random function to do this random split. By the way, just to mention, many people suggest how do you get random data from Transact SQL using new ID function. Crypt-gen random gives you better distribution. It gives you actually Gaussian function, while new ID gives you uniform distribution, which could be good in some cases, but I prefer to have really statistical random. So I would suggest that you use this one, crypt-gen random. So I have 5,045 rows in my test set, and the rest will be the training set. So I will just use where not exist to add the other part of data set in the training set. So I will teach the models using nearly 13,000 cases, and more than 5,000 cases will be used for test. I can even copy this number. I will use it later. Now let's also add, I will just add primary key on customer key and also non-clustered index on grouping factor and bike buyer. So I will have very, very fast access to a distribution of bike buyer inside a group. Okay. Now let's do some predictions, and I'm setting statistics time on. For KNN, I told you it is not too good for Transact SQL. I use it mostly to introduce lookalike. So what I'm doing, I'm reading the data from test set, and I'm checking average of bike buyer for from the training set. I'm using outer apply. So for every row from this set, I'm selecting top 10 rows based on geometrical distance, which is implemented in the ST distance method of geometry data type. And top 10 ordered by this distance. And of course, this varies that I don't get the point itself back. So, okay, and then let's check this and let's execute. And this will last, usually it takes around 40 seconds. Of course, I don't have any index. So basically for every row from test set, I am scanning full training set, sorting it, and then selecting top 10 rows. So basically, I am doing kind of cross join. So yes, I said lookalike model. We don't have, not lookalike model, KNN algorithm. We don't have loops, but what we have initially is a cross join. And let's see when it finishes, how can I improve it with index. It's still executing 50 seconds. I guess this is because we are now on Teams, so it uses some resources. Anyway, usually it was elapsed time around 40 seconds, CPU time couple of times higher because it uses parallel scans. I will just stop it. It's already more than 1 minute. Okay, it just stopped. This is because of Teams. You see, now it was elapsed time was a minute and 15 and 3 times higher CPU time because of parallelism. And I was hoping that we could help ourselves with spatial index on geometry type with this bounding box. Remember minimal, maximal values of scaled variables. And let's do the predictive queries again. Just to say immediately, don't expect too much. Usually I get twice faster execution. You would say that then these indexes, spatial indexes, are not so useful. They are not so useful for this task. They are not, they are actually giving also a lot of what is called false positives. So what you do is, what they do, they pre-select, let's say, points that are in, they split data into boxes and they pre-select points from one box, only not from, let's say, if we have 16 boxes, it's still 16 times less cases, but then we still have to scan all of this. So we are still doing some kind of cross join, just with less cases in the training set. So elapsed time is nearly 3 times faster. CPU time, still high parallelism was used. A little bit better, but not really useful on huge data sets. Okay, with samples, you can use it. But please note, we used only 2 input variables. So now I will just do the predictions, and then calculate the accuracy. I will create this confusion matrix. So unfortunately, this will take another 40, 50 seconds. Please note that I used only 2 input variables, long execution. So also I do not expect extremely good accuracy. Still, it should be better than random guess, better than 50-50. And you see, I did it a couple of times, but I will get, since the split was done randomly, I will get different results. So I have true negatives, and I have true positives. And then what is here is simply the total number. Sorry. I copied again. I wanted to copy this total number of test rows. So I wanted to make this faster. I should copy first this number. And let's see the accuracy of this one, 60% better. This is quite good lift considering original distribution and considering we have only 2 input variables. Still, I'm not over satisfied. So let's do the lookalike model. Remember, we have a training set which has grouping factor and has non-clustered index over grouping factor and target variable bike buyer. So I can extremely quickly find the appropriate group and then simply calculate average of bike buyer, and this is my probability. And if probability is greater than 0.5, I will declare this as a buyer, otherwise as a non-buyer. And here are my predictions for the full test set. Now, this was done in 0 time. Actually, didn't use statistics time anymore. You can see here that it is less than half a second. So this is something that is useful. This is useful. Remember, I used 4 input variables. I could use more, but then I would get more groups, which could be less useful. So this is grouping factor, and this is probability. This is the actual bike buyer. This is predicted buyer, and this is count of cases in these groups. I should also filter if there is count lower than 10, simply filter those out because they make no sense. But for the sake of simplicity, I am just going to calculate the accuracy. And let's do it. So first I need this number, right? And then true negatives and true positives. And check the accuracy. And this time it is nearly 63% better. You see, on previous test, I even get practically 67%. Now, this the difference is because, of course, random split. 67%, even 63 is good number. 67 is very, very good. Why am I saying this? Did you notice how fast it was? Now, on the same data set, I played with R, with different algorithms, with decision trees, with neural networks, and so on. And I could barely get more than 70% accuracy. So basically, I would say fantastic result, especially this one, which I couldn't repeat. Okay. Let me be fair. I tested this many times, and such high result was only once. Usually, it's around 63%. So this is more accurate, but it's still pretty good because did you see how fast it was? And data preparation and everything. Now, this is something that can be used on really, really huge data sets. And now I will go and introduce another predictive algorithm, Bayesian Inference or naive Bayes. This is also an algorithm that is pretty fast. This is an algorithm that, unlike decision trees, doesn't have loops built in algorithm. So similarly, like I started by formally naming decision trees recursive partitioning, I will formally introduce Bayesian inference and then explain in a lighter way how it works. So officially, Bayesian inference calculates probabilities for each possible state of the input attribute given each state of the predictable attribute. And then these are used for predictions. So what we are doing is the opposite thing as with decision trees or lookalike model. Remember, there we calculated distribution of target variable in classes of input variables. Now we turned the direction. We are calculating distribution of input variables in classes of target variables. Now let me do a little bit more human explanation, and then we'll go back to mathematics. So let's say that I'm buying a second-hand car. And initially, I know this from car magazines, 30% of second-hand cars are faulty. I have no clue about cars. And this is not just for this example. I really have no clue about cars. So my initial probability to get a good car is 70%. But I have a friend, a mechanic, and this friend, let's say, decided to take a quick drive with me. And this friend is pretty good of finding faulty cars. So if car is faulty, in 90% cases, my friend will declare it as faulty, and in 10% of cases, incorrectly as good. For good cars, my friend will be wrong in 20% of cases. They will be declared as faulty, and in 80% of cases, they will be declared as good. So altogether, my friend will judge 41% of cars as faulty and 59% as okay. And now we use these reverse probabilities. So if we look out of this 0.59, 0.56 are really good and 0.03 are bad. So my probability that after my friend judged that a car is okay, that is really okay, is 0.56 divided by 0.59. So these are these reverse probabilities, and this means that after my friend judged the car as okay, posterior probabilities for me is 95% probability that this is really okay. Now this was single input variable, my friend, or declaration of my friend, single input variable, but we can have multiple input variables, and let's calculate distribution of input variables in two classes of bike buyer. So I have region, I have number of cars owned, no, 0 is non-buyers, 1 is buyers. So we have here stacked bar chart, here we or stacked column chart, we have here clustered bar chart and another stacked bar chart. I actually created these charts in Power BI. And we have this distribution in three input variables in classes of target variable. Now, how do we calculate? What we need is probabilities out of these likelihoods. So if I go back here to my friend, remember, this is likelihood 0.56. This is likelihood for positive state, 0.56 out of 0.59. It was simple to calculate probabilities when we have single input variable. How do we calculate with two or more input variables? So I have here a region and number of cars owned, and let's call these results A, B, C, and D. So these 4 values. So A means distribution. So we have 23.6, 23.7% of people with a single car for non-buyers, with a single car for non-buyers. And we have, for non-buyers, we have 14% of people and 15% from Pacific. For buyers, we have 29% of people with a single car and 23% of people from Pacific region. These are likelihoods. These are terms A, B, C, D. How do I get posterior probabilities for 2 variables? A multiplied by B divided by A multiplied by B plus C multiplied by D, and so on. If I have more variables, I simply add more multiplications. Now, what I need here is I will get a table like this, a table where I will have these values in rows because we work with tables, and then I will have to do aggregation of these values. But this will be aggregate product. And of course, we don't have aggregate product in Transact SQL. But we can very, very easily get it if we use a little bit of mathematics. We know that in mathematics, logarithm of A multiplied by B is logarithm A plus logarithm B. So if I summarize logarithmic values, then I get logarithm of product. And then I simply use the opposite function, inverse function, exponential, to get the actual probabilities. Now we have all theory, so let's go and check the model. So we already have training and test set. Let's just do union of both of them and see what we have. So I have grouping factor, I have couple of variables. I didn't select all of the data. I will just use now 3 input variables for Bayesian inference, which is less than 4 in lookalike model. So I expect a little bit worse accuracy. But I didn't want to have too many because it would be then hard to follow or how queries work based on that mathematics. Now, let's say for bike buyer equals 1, I am calculating the distribution of region. And again, I'm using cross join to simply add the total count of cases in this class for bike buyer equal 1 from training set. Remember, I have approximately 13,000 cases there. So this is distribution of region in training set for bike buyer equals 1. And I got these numbers. Remember, Pacific, these are the actual numbers. And let's do calculation for both both bike buyer equals 1 and bike buyer equals 0. But let's do also calculation for region, number of cars owned, and commute distance. I will use group by grouping sets, all these 3 variables, and then the same thing for bike buyer equals 0. And I will let's do the full calculation. So you see these are 26 rows. This is actually my model. It's not stored in a table, but this is actually my model. I just implemented a Bayesian inference algorithm on my training set. Remember, we have the same variables in test set. Just to repeat, we have 55, 46 rows in test set. Now I am actually creating the model. Remember, model means implement an algorithm on dataset. With lookalike model, we actually didn't have the model. Training set was our model. Now we are creating a new table, which is a model, but we are still passing through data only a couple of times with grouping sets. This is as efficient as it can be. And this is my model. This is my model, 26 rows. And now I can select region Pacific, number car sold, one example. So these are distribution. This is distribution in classes of bike buyer 0. So I have nearly 15% of people with commute distance from 2 to 5 miles. And then this is an example how I could do manual calculation, but remember how we can calculate aggregate product. We summarize logarithms of values, then we use some function which we have, and then we do the reverse function exponential. So let's do prediction with variables. So I will store result negative percentage in NPCT and positive percentage in true PCT, TPCT variable, and for these selected cases, right? And then I will calculate this manually. So everything here. So for this example, region Pacific, number cars sold 1, commute distance 2 to 5 miles. I have this negative and positive likelihood and positive and negative probability. So I have more than 72% probability that a person that is from Pacific region with a single car and commutes for 2 to 5 miles will be a bike buyer. Now let's do the prediction query out of this. So I will just, okay, for this moment, still fix, but I am doing prediction query without variables. So just predicting one value, in this case, a positive outcome. Now I will parameterize these 3 parts of where clause. I will parameterize and create a function. So I will have input parameters, region, number of cars, and commute distance. And this one will do then full prediction on input data. Step by step, we have function, and from here it is extremely simple. So I'm now using full test set, and I'm just applying the function, which uses arguments for parameters, data from the test set. And here are my predictions, actual value, predicted positive probability, and predicted value. And of course, I can again calculate accuracy. Classification matrix. Let's hope that I didn't lose my total number of cases in test set. So let's calculate the accuracy. And it's more than 61.4%. So again, pretty good with very, very good performance. So if I now evaluate all models, so okay, KNN is still not very useful. On samples, maybe yes. But with spatial indexes, the results are not so much better. Performance, it's not so much better as you might expect with classical non-clustered indexes. So that's why I also used 2 input variables only. Actually, this is also a limitation of geometry data type. If I would use more than 2 variables, I would actually even need to create my own calculations. Anyway, this is hard to optimize. There are not many loops, but still not extremely useful. Lookalike model gave us very, very good results. Again, don't think that this accuracy was bad. I told you with the best algorithms I could get in R, I could hardly reach 70%. Bayesian inference, I could get also better in accuracy with more variables. I didn't want to include more variables for the sake of simplicity of the code. It was slightly slower than lookalike model because there was actually some training. So I did a grouping of data. This was training and storing this into a new table, which was our model then. And with grouping sets, I still probably needed as many passes through data as I had input variables, because I don't see how SQL Server could perform two groupings in a single pass. So let's say if we would have 5 input variables, we would have 5 scales of data. Okay, not too good, but still acceptable. Still, it would be faster than anything in R or Python. But with number of input variables, this would the performance would then, of course, linearly drop. Linearly is okay. I mean, linearly, twice faster hardware means you can afford twice more variables or 2 times more input cases. So let me now check. Okay, all my teams, the chat link doesn't appear. If you go up in the chat, I will just copy and paste it again. So I will just, you see what I'm doing, it's here. So it should be here. Otherwise I can, Eddie Cruz, Eddie, I can, or maybe Jan could send you over email. But maybe you just didn't see. You also, Fermin, you should now see the link. And another share, okay. Yeah, you got the links. Okay, so then we have a question from Michael. Can you also leverage the system calculated table statistics for fast calculations? This one is actually what is statistics doing? By default, it is using sampling. And I could manually create statistics, and then it would be actually something very, very similar to lookalike model. I think, yes, with full scan would actually do the same thing as I would do. And you can get double result from DVCC show statistics. So yes, you could do it. You could do it, and then let's say it would be kind of one step less. No, it wouldn't be one step less. You should still create index separately and statistics separately, because the full statistics is only for the first column. So it would be the same from performance point of view, but a little bit more complex. But very, very nice question.
Good presentation, Shaka. I'm happy I have you today, and also thank you for putting this together.
You are very welcome. I was very happy to be here. Okay. Oh, if you are running this on SQL Spark Elastic Pools, can you explicitly optimize use of the additional horizontal scaling? I think you could scale based on some, let's say, Bayesian inference. Maybe you could do horizontal scaling based on target variable. And then I see Oli. Thank you. So thank you everybody for being so nice and being with me. And it is also recorded, so also people that couldn't join will be able to watch it later.